I am going to talk today about sampling and in particular Markov chain Monte Carlo methods. As you can see here, we are going to discuss one method in particular named Hamiltonian Monte Carlo, which is a widely used sampler that I'm going to do a short summary about it. And we are going to talk a bit about the robustness issues of Hamiltonian Monte Carlo. The word robustness here relates to the robustness of tuning of the parameters of Hamiltonian Monte Carlo. And we are going to study the Langevin diffusion or kinetic Langevin diffusion as a way to introduce randomness in the trajectories that will enable robustness of tuning with respect to its parameters, right? So the resulting algorithm is named Metropolis adjusted Langevin trajectories, and I'm going to try to convince you that it can yield a robust alternative to Hamiltonian Monte Carlo. This is a joint work with Riou-Durand from the University of Warwick. He's a postdoc as well. And I'm going to split my presentations into three parts. First, I'm going to do a short recap about what is Hamiltonian Monte Carlo, but I am also going to discuss about some problems of robustness of tuning for HMC, and I'm going to introduce some solutions suggested in the literature to tune its parameters and to ensure robustness of tuning as well. One of these methods is known as randomized HMC, where you draw the length of the trajectories at random at each iteration. This is a way to introduce randomness within Hamiltonian trajectories that yields robustness of tuning that we are going to illustrate at this point. And then we are going to motivate a bit our study that is built upon the Langevin diffusion. So the Langevin diffusion here relates to several names in the literature, such as kinetic Langevin diffusion or second order Langevin or undamped Langevin. There are many names. And we are going to illustrate why this stochastic process can yield an alternative to randomized HMC, an alternative way to introduce randomness in the trajectories and therefore ensure robustness of tuning. We are going to connect the two approaches and to compare the two of them in terms of exponential mixing rates. And then we are going to introduce the algorithm built upon this diffusion process, this Metropolis adjusted Langevin trajectories or MALT algorithm. And we are going to illustrate its efficiency both from a theoretical viewpoint through the study of scaling limits for this MALT algorithm, but also through numerical experiments. Let us start with a few notations. So these are simply distances and metrics or norms that I'm going to refer to during the talk. And here we are. So the goal here is to sample approximately from a target distribution with density with respect to Lebesgue's measure on RD. This density would be denoted pi here. And as you can see, we assume something here. We assume that it is positive everywhere. Another way to assume that is simply to specify its minus log density phi here. And this function phi will be called potential function. Okay, so we are going to assume that this function phi is actually smooth. It's differentiable, and its gradient is Lipschitz smooth. Okay. Right, and we are going to focus on one particular method, sampling method, approximate sampling method for sampling approximately with respect to pi, that is built upon Hamiltonian dynamics. Okay, right. So there are many ways to sample approximately according to pi, but so there is one main branch of research concern Markov chain Monte Carlo methods. And the principle of these methods is to construct an algorithm that actually is simply a Markov chain that will converge in distribution towards pi as you let the number of iterations go to infinity. Right? And so one of these MCMC algorithm is this Hamiltonian Monte Carlo algorithm, and it is built upon these dynamics. And these dynamics, as you can see, they relate to the motion of position x and a velocity v on a space. And if you start from x0, v0, what will happen by following the solution of this ordinary differential equation is that you will follow the contours here of a target with density pi star. So the contours of this density pi star, which is density on an extended space. So as you can see now, there is distribution for the position. This is target distribution pi, and there is now also a distribution for the velocity, which is a Gaussian, standard Gaussian distribution. Okay. So one property of these dynamics is that they preserve this measure on an extended space, pi star, in the sense that if you start from x0, v0 distributed according to pi star, then for any positive t, xt, vt will still be distributed according to pi star. Right? So in this sense, Hamiltonian dynamics leaves pi star invariant. Of course, well, these dynamics cannot yield an ergodic Markov process simply because it is completely deterministic, and you will just go around and around. If you start from a certain x0, v0, you will never converge in distribution towards pi star, right? So to be able to converge in distribution, you need to introduce some randomness at some point in the algorithm. Okay. So before introducing the algorithm, let us note that Hamiltonian dynamics in almost all situations do not have closed form solutions. So instead, we use an integrator to approximate these dynamics, and probably one of the most famous integrator is known as the leapfrog method, or the Stormer-Verlet update. And it is built upon a simple principle. You will split Hamiltonian dynamics into two parts. First, you will follow the motion of the velocity for half a step, where h is the step size, right? Then you will follow the dynamics of the position for a full step, and then you will compose again with following dynamics of the velocity for half a step. Right? So if you combine these three steps together, you get the leapfrog update, and you will now build a trajectory, or shall I say a numerical Hamiltonian trajectory, by composing all these steps L times, where L is chosen roughly to be the integration time divided by the time step. And so built upon this discretization, Hamiltonian Monte Carlo was introduced in 1987, and the principle is the following. You start from a fresh Gaussian noise, V prime. You choose a certain time step h and integration time t that are fixed along the algorithm here. And you will propose a certain trajectory, Hamiltonian numerical trajectory, for a certain number of steps, L to be c over h. And you will accept or reject this trajectory with certain probability, right? And so this accept-reject mechanism is known as Metropolis Hastings correction. And here you can see that the probability is simply the ratio of the densities after and before the trajectory. Okay. And so I added the last step, as you can see here. And this last step shows that if you reject, you should flip the momentum. So you might say, well, as you can see, this is a remark here. The fact that you have full refreshments at every iteration, actually, it does not matter if you put this last step or if you don't, right? So the reason why I put this last step is that, well, it is to highlight the fact that to build an algorithm that has the right stationary distribution here, we actually compose two Markov kernels. Right? So the first map of kernel is the refreshment of the velocity that preserves pi star, since V prime is distributed to a Gaussian distribution in pi star. And the second kernel is the composition of these three steps here. That is a Metropolis correction for time reversible trajectories, such as Hamiltonian trajectories. Okay. So you might say, this is of little importance. Why talking about this for 2 minutes? That's a good question. Well, here is one of the answers. A few years later, in 1991, a generalization of HMC was introduced. So it's called GHMC. And you can see here that it's very similar to HMC, except it involves now a certain parameter alpha that will be related to a certain notion of persistence, right? So as you can see here, the only difference is that the refreshments are now partial, right? So if alpha is equal to 0, you recover the full refreshment, therefore you recover the standard HMC algorithm. But now, as soon as alpha is strictly positive, you can see that the flips of the momentum are not erased, or at least they are only partially erased. Right? This was a bit upsetting because, well, this algorithm did not receive as much interest as the standard HMC algorithm, I think it is fair to say. And it is also a pity because one motivation of this paper was also to connect to the kinetic Langevin diffusion by choosing a certain persistent parameter here quite close to 1 in a way that we will make it explicit later. Okay. Right. So now I'm going to focus a bit about the choice of parameters H and T. And we are going to assume, for simplicity, first that alpha is equal to 0. Okay. So alpha is equal to 0, just full refreshment, standard HMC, and we want to choose these parameters. How can we do that? So there are several works that study this question in the literature. I'm just going to focus on 2 of them. The first one is a result by Beskos and co-authors in 2013. And it relates to a series of papers on the scaling limits of MCMC algorithm. Right. So what is the goal here? Well, the goal is to study the acceptance rate of the MCMC algorithm. So as we discussed, there is a Metropolis Hastings correction, and so there is a accept-reject mechanism, accept-reject test at each iteration, and we would like to know how this acceptance rate behaves when dimension goes to infinity. Right? How can we choose a time step such that the acceptance rate does not go to 0 and the algorithm gets stuck, right? So here the main assumption here is quite strong, as you can see, because it is simply assuming that the potential function writes as a sum of individual functions. Right? So it boils down to assuming that the posterior distribution is actually product form, which boils down to assuming that all the components are independent. Right? So of course, this is quite unrealistic. But here you can see this assumption more as a convenient way to have a mathematical framework that allows the study of the acceptance rate as a function of the dimension when the time step is chosen itself as a function of the dimension. Right? And so if you want to get an asymptotic acceptance rate that does not vanish, right, that is non-trivial, that's strictly between 0 and 1, actually the right choice of time step is to choose a time step that decays to 0 as dimension goes to infinity at this rate, dimension to the -1/4. And the framework is sufficiently neat such that there is an explicit optimization possible here for certain measures of efficiency. And there exists an optimal constant here. So there is an optimal choice of asymptotic time step, if you prefer, such that the corresponding acceptance rate is approximately 65%. So that gives actually 2 information. First, it's quite a useful tuning guideline that is very easy to implement because monitoring the acceptance rate out of an MCMC algorithm is very easy. And the second one is that it gives us some information on how many gradient evaluation we are going to need if we want to approximate a certain trajectory of physical length t, say, right? So here the answer will be d to the 1, 4 for product form targets. Okay. So it gives us some information about the complexity of the algorithm in high dimension as well, at least in this optimistic framework. Right. Now I'm going to talk a bit about the choice of the integration time, because it is quite known that HMC is sensitive to the choice of t. And one method that has been suggested in the literature is the so-called no U-turn sampler. So this method is adaptive tuning solution for HMC. So I point out this one, but there are many others that follow a similar principle, or at least that aim for similar strategies. And here, without going into the details, I'm simply highlighting the fact that the idea is to follow Hamiltonian dynamics up until a certain criterion is met, a stopping rule. And the stopping rule actually relates to simple computation of the motion of the norm between xt and x0 as t evolves. And actually the distance between the original point x0 and xt, as you can see, the square distance, will increase as long as the scalar product is positive. And therefore, an idea, if you want to select t that will result in points that are further away, is to try to follow these dynamics until this criterion is met. Now, of course, there are some technical details that are not presented here to ensure that the algorithm has the right stationary distribution. So there is a whole recursion to explain. But I'm just going to point out here that these algorithms and other adaptive tuning solutions provide black box for tuning t, and therefore they receive a lot of interest. And also they aim to maximize here Euclidean jump distance. Right? So if you are happy with this criterion, then that's perfectly fine. Now we are going to illustrate that the choice of the Euclidean metric does not give particular guarantees for a given component, say. This is not really inherent to adaptive tuning solution. This is more inherent to a fixed T strategy for HMC, and I'm going to illustrate this here. Right? So this is actually well known for HMC. You don't have to go very far to see that HMC with fixed choice of T can struggle. You can just take a Gaussian example with heterogeneity of scales. You have various sigma i's here, and you have a bunch of Gaussians, independent Gaussians with different variances. And we plot here the so-called autocorrelations functions, right, or ACF. So these functions, rho I of t, are functions of the integration time. And they correspond to the autocorrelation between xi of t and xi of 0, right? So we want this correlation to be as close as 0 as possible. You can think about this ACF as the first order autocorrelation of the chain. Well, simply because at each iteration, we produce a trajectory of length t, and we accept or reject with a test, right? And we so on and so forth, right? So if these correlations are close to 0, then we produce uncorrelated samples, and therefore all the estimators built on the Markov chains eventually will be more precise. Yeah. So in the Gaussian case, as you can see, everything is explicit, and all these ACFs actually simply boils down to cosinus function with different bandwidths. And so now if you ask yourself the question, how could I choose the value of t that will control all at once these autocorrelations? You can see that, well, you can't really in a lot of situations, in the sense that the maximum, right, the maximum absolute ACF as a function of t can be an arbitrarily erratic function and can be arbitrarily close to 1 as well. So that's a problem, right? Because we could be happy to say that the Euclidean square jump distance is the maximum we can get, but if for a few components we cannot guarantee that there will be good mixing, well, that's a problem, because in a lot of situations we would like to be sure that really for all the components without any without looking particular or on how big the scale is. We would like to be sure that there is good mixing for them. So the main solution suggested in the literature to tackle this problem is to introduce randomness in Hamiltonian trajectories by selecting the integration time at random. Right? So here I point out one reference that chooses this exponential distribution for the integration time, but this idea is not new, right? So they're already in the book of Radford-Neal in 2011. You can find similar suggestions with uniform distribution. You can choose different choices of distribution here, but the principle is more or less always the same. The goal is to introduce an averaging, smoothing effect on the autocorrelations. And as you can see, if you compute here in the Gaussian case the expected correlation, you get something now that is monotonic and that can be controlled over I. Right? So we get a uniform bound that is monotonic and decays as lambda minus 1 goes to infinity. So just recall that lambda minus 1 is the inverse. Right? So lambda is the inverse of the expected integration time. Okay. Right. So that's well, that's great because it gives us a way to get robustness by selecting t at random and tuning the average of t instead of tuning t. Right? We are going to motivate now the study of a diffusion process that yields an alternative to randomized integration time. And this diffusion process is built upon the following SDE. It's known as the Langevin diffusion or kinetic Langevin diffusion, or underdamp Langevin diffusion as well. And as you can see, it is built as a construction. You can split here this SDE into two parts. The first part just boils down to Hamiltonian dynamics, right? And the second part here correspond to a certain what's called Ornstein-Uhlenbeck process, right? So it's just a Gaussian process. If you look at the motion for the velocity here, right? And there is a parameter involved. This parameter is denoted gamma, and it's called either damping parameter or friction. Okay. So you can see actually these dynamics, known as Langevin dynamics, simply as a mixture of Hamiltonian dynamics with certain refreshment of the velocity. But here, the refreshment of the velocity is done continuously, right? And it's induced by a Brownian motion. Right? So it's not a fixed time, it's just a continuum refreshment of the velocities. And so this gamma parameter measures how fast the refreshment will occur. Right? So these dynamics preserve the same invariant measure by star. That's quite clear from the definition here, since each of these two preserves by star. And we are going to look at the same running example, this Gaussian target with heterogeneity of scales. And we are going to plot here the ACF we can get for the kinetic Langevin diffusion. First, we are going to study it for different choices of frictions, right? So first, we will just fix the scale equal to 1. So you can, it's just an isotopic target, or you can just think about it as one-dimensional target if you prefer. And we just plot all these ACFs for different values of frictions, right? So gamma is equal to 0 correspond to this periodic cosine function, as you can see here. And then you can see that, well, there are different behaviors depending on the choice of the damping parameter gamma. So when gamma is between 0 and 2, what happens is that the ACFs have oscillatory decay to 0. And above 2, well, the ACF have monotonous decay to 0. Right. So the long-term convergence is optimized actually for this choice of friction that separates these two regimes, right? So we are going to call these two regimes the underdamped regime when gamma is smaller than this value, and the overdamped regime when the friction gamma is higher than this value. So the long-term the long-term exponential convergence is actually optimized for this critical choice of damping, gamma equal 2. Now, of course, if remember that T here will be a certain measure of the computational complexity for generating a trajectory. Why is that? Because in practice, if you choose a time step h, well, you will compute T over h gradients, right? So your number of gradient evaluation will be proportional to T. So if you manage to reduce T for fixed time steps, say, well, it is cheaper for the algorithm to produce these trajectories. And so, of course, if you want to get uncorrelated samples where there is no choice of friction or positive friction that can beat the choice gamma equals 0 to obtain uncorrelated samples as fast as possible. Right? Okay. So this is quite well known, actually. But now let's plot the same autocorrelation functions, but now for fixed friction and for various scales sigma I. Right? So here we plot what happens for the kinetic Langevin diffusion for gamma equal 2, this critical choice of damping, and we compare it to what happened for HMC when gamma is equal to 0. This plot we already saw a few slides ago. So on the right-hand side, as you can see, well, depending on the scale, you have different behaviors, right? So when the scale is lower than a certain reference scale, sigma equal 1, well, you get oscillatory decay towards 0, but all of these autocorrelation functions are still dominated by this reference, by the ACF corresponding to the reference scale sigma equal 1. However, if you choose scales that are higher than this reference scale, then they will have a monotonous decay, but they will decay much slower than for the reference scale. So this observation gives us actually a nice way to tune the friction parameter here to control all the correlations at once. And how to do it? Well, if you choose this friction to be equal to 2 divided by the maximum scale, right? So that's just boiled down as assuming that the reference scale is just the largest one. Well, what you obtain is a uniform control on all these maximum absolute ACFs as function of T that yields a bound here that decays in the monotonic way. Right? So inducing randomness in the Hamiltonian trajectories through this continuous momentum refreshment rather than selecting T at random for HMC is another way to ensure robustness of tuning in the sense that you can choose now a certain value of integration time that will control all the autocorrelations at once, and therefore the mixing, the efficiency of the sampler for every component. So before building the sampler itself, we are going now to relate a bit this diffusion process with another continuous time Markov process. And I apologize for all these equations. I'm going to say a bit about each of these points. First, let's forget about the point in the middle, and let's just focus about the points above here. Right? So here we simply denote what is the randomized HMC stochastic process, right? Continuous time stochastic process. So randomized HMC, as you can see, it's very similar to HMC in the sense that there is this Hamiltonian dynamics here, and then there is a source of refreshment here that is induced by a Poisson process, NT, instead of a Brownian motion. So the difference with the kinetic Langevin diffusion here is that the refreshments are done in a discrete way, and there are two parameters for that. The first one is a lambda parameter that denotes the intensity of refreshment. So the higher lambda is, the more frequent are these refreshments. And then there is this alpha parameter that we already know, this persistence parameter that controls how partial the refreshment will be. Right. So when alpha is close to 1, it will be more and more partial refreshment. Okay. Right. And the second point is simply a way to say that the distribution of these stochastic processes, both randomized HMC and the kinetic Langevin diffusion, can actually be characterized by what are called infinitesimal generators. Okay, so what are these objects? Well, they relate to the expectation of a certain test function starting from a given point. And we have to differentiate these expectations to get formula for the generators. But the important part is that it characterizes the distribution of the stochastic process. And as you can see here, well, both randomized HMC and the kinetic Langevin diffusion have generators that are built on three stones, right? So there are three different stones. The first one is a common stone, is the generator of Hamiltonian trajectories. Okay, it is defined here. And then they have two different sources of refreshment. So that's a nice way to write these. And so they have a common dynamics, common Hamiltonian dynamics, and then there are two different sources of refreshment. The first one is a source of refreshment induced by a certain Poisson process with an intensity lambda and with a persistence parameter alpha. And the second one is refreshment induced, continuous refreshment induced by a buoyant motion with a certain speed of refreshment, gamma. And actually, we can relate those two generators and show that the difference of these two generators for test function f converges to 0 for a certain choice of intensity of refreshment as a function of alpha when alpha goes to 1. Okay, so when you choose a refreshment here that will go to infinity at a certain rate here, when the alpha parameter goes to 1, actually, the randomized HMC process converges to the Langevin diffusion. Okay, so as another way to say it is simply that the kinetic Langevin diffusion is a limit of randomized HMC, and it's obtained when refreshments becomes more and more partial and frequent. Here we study the mixing rate. Here, the exponential mixing rate in both Wasserstein distance and L2 norm. Right? So it is a way here to measure how fast the stochastic process will converge to the stationary distribution if you start from any distribution nu. Okay. Right. And to obtain explicit rate of convergence, well, we have to assume some relatively strong assumption on the potential. And in particular, here we assume that the target distribution is strongly log concave, which boils down to assuming that the Hessian of phi here has all its eigenvalues that are greater than constant, positive constant m. And the right-hand side actually just boils down to assuming that the gradient is Lipschitz. So there is nothing new. It's the right-hand side here. Okay. And now we are going to focus here on the rates we obtain, R, right? So the bigger the rate is, the happier we are, because it means we converge to pi faster. And as you can see here, these rates, so these are upper bounds, it's true, but you can see that this rate here is an increasing function of the persistence parameter alpha. Okay, so it's explicit with respect to the constants of the assumption, small m and capital M, but also with the persistence parameter alpha. And its optimal value is actually obtained as a limit when alpha goes to 1, as you can see. And you can also see that here the choice of intensity of refreshments that maximizes the upper bound that we get on this rate is a certain function that goes to infinity as alpha goes to 1, just the same way as we noted on the last slide, right? So actually this illustrates that the Langevin diffusion can be seen here as a limit of randomized HMC, but also that achieves the fastest, at least the best upper bound to our knowledge on the exponential mixing rate for strongly log concave targets. Right? So another way to say it is that if you want to optimize these rates, or at least the upper bounds we get on these rates over both lambda and alpha, somehow it pushes you towards the kinetic Langevin diffusion. Okay. So as I said, this is an interpolation of results from Alexandre Bouchard-Coté and George Eligianidis and co-authors, and also a result that we study with Anna Daradian during my thesis. And it motivates here the construction of a sampling algorithm directly built on kinetic Langevin trajectories and to motivate also the study of theoretical properties of this algorithm, but also it motivates the comparison with randomized HMC. Let us introduce this algorithm at last. Well, it is built, as you can see here, on a certain time discretization that is very similar to the leapfrog method. So I'm not going to expand too much on this. As you can see, the 3 steps in the middle just boils down to the leapfrog method, and you add on top here and after some partial momentum refreshment with a value of alpha that is fixed here, right? It's no longer a free parameter. It's quite close to 1 when h goes to 0, and it is fixed by the friction and the time step h. Right? So when you do that, you recover a discretization of the kinetic Langevin diffusion, and you can compose L steps just as you do for Hamiltonian trajectories, but now you recover numerical Langevin trajectories. We are going to call this. We're going to denote this update by a Markov kernel QH gamma, and the QH gamma to the L will be simply the notation for the F composition for this kernel. So the algorithm we introduce is defined as follows. As you can see, it is very similar to HMC. We start with certain fresh Gaussian noise, V0, and now we propose numerical Langevin trajectory. Right. And this numerical Langevin trajectory will be accepted with a certain probability that corresponds to Metropolis accept-reject mechanism. And as you can see, this probability here can be written. So there are several ways to write this acceptance probability, but one way is to write it as a product of these 2 things, where on the left-hand side we have actually what we compute for HMC. On the right-hand side, we have here a ratio of the densities of the forward and backward trajectories with a minus sign here on the numerator when looking at the backward trajectory. Right. So just as for HMC, the number of gradients evaluation to run this algorithm is roughly L. Right. Why is that? Because, well, in this big product here, well, there are some gradients involved, it's true, but these gradients are exactly the same as we have computed for generating the numerical Langevin trajectory. So in that sense, you do not require more gradient evaluations that you do for HMC. Okay. Just as HMC, you can see that the momentum flips that ensure that these 3 last steps preserve the right stationary distribution, while these flips are erased completely by the momentum refreshment, which was not the case for GHMC, for positive alpha. So I wrote a few points here. So the first thing is that we present this algorithm as call it a neat Metropolis adjustment for the Langevin diffusion. This is to compare actually this algorithm to the choice of GHMC, right? So in particular, this choice of algorithm GHMC, when you choose a persistence parameter that is very close to 1, suffers from several problems. And we argue that this can yield an alternative that is quite sensible, because we can here choose the length of the trajectories, and because momentum flips are erased by full refreshment. So in particular, for a choice of friction that is positive here, the trajectories are ergodic. So if we compare to deterministic Hamiltonian trajectories, you can no longer suffer from what's called U-turn, which is a waste of computational resource. If you run a lot of steps, at some point with Hamiltonian trajectories, you're just go back to your original points, and you'll get quite high correlation, but you will have spent a lot of resources for nothing. So these type of things do not really happen. What happens is that, of course, it will become more and more expensive when the integration time is chosen to be big, but at least the points proposed will become more and more uncorrelated. So we have illustrated the fact that positive damping can enable controls of the worst ACF and therefore enable robustness of the choice of integration time t. And we illustrate in the next slide that actually this algorithm enjoys similar properties to HMC when studying its scaling limits. In particular, we recover the dimension to the 1/4 scaling for any choice of friction without additional assumptions. Right? So this is the point of this slide. Under the same framework, without additional assumption, which are already strong, we get that the optimal choice of time step is to choose time step that decrease as dimension to the -1/4, and we get similar tuning guidelines. So it's a tuning guidelines here of h given t and the friction gamma, which is that you can simply monitor the acceptance rate and try to tune it around 65%. So this yields an extension of the results of Pescos and co-authors to any choice of friction, and as I said, it does not involve any additional assumption. Finally, I'm going to illustrate the performance of this algorithm and compare it a bit with randomized HMC. So there are some investigation as well. So here is an illustration on the Gaussian case. In the preprints, you can find some investigation on other types of targets, including stronger concave targets, but also heavier tail targets. This is an illustration for sure, but it's a nice way to visualize the typical problem that HMC with fixed T will suffer from, and to visualize how MOLT and randomized HMC will compare when estimating the mean and the square function. Right? So here we consider first the gray curve. We are going simply to say what is the gray curve here. The gray curve corresponds to what HMC would do if the target was isotopic. So this is another way to say it is to consider what HMC would do if it was perfectly preconditioned here. Right? Okay. So when it's isotopic, it's as we discussed, well, it's quite easy. There is one choice of integration time, which is pi/2 that will yield simply independent samples, and therefore all the efficiencies can be compared to what happens here, because we just note it equal to 1 when this is the case for HMC. Okay. So we rescale all these effective sample size by the time such that they yield a sensible measure of efficiency, of course. And we can see here that there are different behaviors between MOLT, randomized HMC, and HMC when we introduce heterogeneity of scales. Right? So we look at the same Gaussian example, and we look now at heterogeneity such that the ratio between the highest and the smallest variance scales linearly with the dimension. Okay. And we simply illustrate for dimension 50 what happens for ACFs and therefore for the ESS of HMC. As you can see, this is the green curve, and the efficiency is quite an erratic function of T. Right? And actually, it becomes more and more erratic as dimension increases. It is just an illustration for a condition number equal to 50 on typical problems that you can observe for HMC with fixed time. On the pink curve, we illustrate what randomized HMC with full refreshment produce as an efficiency. And this measure of efficiency is the worst effective sample size per time. Okay. So you take all the ESS for all the components, and you just take the worst one. We look at it for estimating the mean and for estimating the variance. As you can see, the difference, there is a difference between the two. And randomized HMC seems to have better efficiency for estimating the mean, and while the other is reversed for estimating the variance. Okay. But both of these functions are quite robust in the sense that a small variation of T will not yield a very big variation of the worst ESS, whereas this is the case for HMC. Okay. Right. So finally, we illustrate this discrepancy more generally between odd and even functions, and we look at a slightly different problem where we fix the time step h, and we want to tune the number of steps L to obtain good efficiency for every function. So H is fixed in a way to obtain acceptance rate that are close to 65% or above. And this is same time step chosen for all of these. And we want to find the L that achieves relatively good efficiency for every function. How do we do it? Well, we did it by simply maximizing heuristically the worst efficiency between estimating the mean and estimating the square. Okay. Right. So if you do that with HMC, actually what will happen for this particular target is that you will find that the best choice of L is L equal 1, because there is no way, as soon as you discretize, to be able to yield here an efficiency that will be non-negligible for estimating the variance. And the consequence of that is that, well, L equal 1 is the best choice you can get, and we simply illustrated what happens for another choice of L to show that you get negligible here, ESS, worst ESS for the even function. And now you can compare what happens for mode and randomization C. You can see that both seems to be quite efficient when looking at this conservative measure of efficiency, the worst ESS. And you can see that mode is better for even functions, whereas randomization C is better for odd functions, although the difference between the two is still within a constant factor. So we cannot really say that one of the methods dominates the other for any choice of function. All right. To summarize, we present the Langevin diffusion as a limit of randomization C that achieves the fastest exponential mixing rate for strongly low-concave targets. We have illustrated that the positive choice of damping can enable control of the worst ACF and therefore enable robustness of tuning the integration time T. We present an algorithm named Metropolis adjusted Langevin trajectories, or MALT, as a neat Metropolis correction for these kinetic Langevin trajectories, because the length of the trajectories can be chosen by a user first, but also because the momentum flips can be erased by full refreshments, as opposed to what happens for GHMC. We support this algorithm with scaling limits, and we show that the optimal choice of scaling for product forms actually connects to the results of Beskos and co-authors in 2013, and we recover the same dimension to the 1-4 scaling for MALT without additional assumption. And this is valid for any choice of friction. We have several perspectives that we are quite interested in. One of these is the question of tuning adaptively these parameters and be able to produce a software implementation that can be competitive with adaptive tuning solutions for HMC. And we are looking forward to do some further comparisons between variations of HMC and MALT, of course, both from a theoretical and numerical viewpoint. Here are a few references, few pictures, and thank you very much for your attention.